Okay, guys, so this is number 3 on your worksheet. We're going to go through this one just like we did with number 1. The problem is a fairly long problem, just like 1, but it is a cooling problem, not a heating problem. So let's go through it. Okay, first things first, make sure that you pick out everything that's important in the question. So we have 125 grams of water, and then it says that water is cooled. That should tell you that it is going to be a cooling curve, okay, not a heating curve. And then we have some temperatures that I want to point out to you. We have 125 degrees Celsius, and we have minus 22 degrees. And then it is asking you how much energy is released, okay? So the heating curve problem, which was problem number 1, okay, you guys should realize that, and let me see if I have my heating curve sample up here, right? So when we have a heating curve, it is going to be considered endothermic. That means that it is absorbing energy from the environment, so all of your numbers will be positive. When you have a cooling curve, that means that it is releasing energy to the environment. That makes it exothermic, so all of your numbers are going to be negative, okay? If you don't get negative numbers on this problem, then that means that you made a mistake somewhere, okay? So let's focus in on number 3. So we have identified all the things that are important, okay? Now we just need to draw our curve. And we've already designated that it's going to be a cooling curve, okay? So let's get to it. So our curve is going to start off the same way all of our curves start off, right? We have both axes. On one axis, this is going to be temperature, and it's going to be in degrees Celsius. On the other one, it's going to be heat. It is a cooling curve, so it's going to be heat removed. Okay? Remember, you need to make note of the important temperatures for water. And our important temperatures, remember, we noted them in problem number 1. They're right here. 0 degrees is our melting or freezing point. And then 100 degrees is going to be our boiling or condensing point. So we need to make sure, since we are doing water, that those are put onto the chart. So I have 0 degrees. Let me put it a little bit closer to the axis there. And then I'm going to have 100 degrees, just like I had before. The problem says we start at 125 degrees. And then the lowest point on our problem is minus 22 degrees. Okay, so now that I have labeled and identified all of the points that are on the problem, now we can actually draw our cooling curve. Okay, so I'm going to draw it in blue. We're going to start at 125. We are going to cool, cool, cool. Let's see if I can make that a little neater for you. We are going to cool till we get to 100. Then the heat that's removed is going to go into converting from a gas to a liquid. And then the energy put in is going to be cooling as a liquid to 0 degrees. And then the heat that's going in is going to go to convert to a liquid, from a liquid to a solid. And then the rest of it is going to be going to a complete solid. So that is our curve, okay? I'm going to try and use the same colors that I used in the last one, just to keep things consistent. So this is going to be E. This is going to be D. This is going to be C. This will be B. And then we are back down at the bottom with A. Okay? Next step is to figure out what equations to use. So let's do this. For E, we are changing in temperature. Let me make sure I keep the format consistent. Q equals mass times the specific heat of whatever state we're in. That is gas. We are in section E of your cooling curve, times the change in temperature. D is going to be Q equals, now, here is the big distinction between a heating curve and a cooling curve. The energy that it takes to create the phase change is exactly the same. So whether I am melting or freezing, or boiling or condensing, the amount of energy that it takes is the same. The difference is that that energy will be negative because you're releasing it, not absorbing it. So what that means for you is your heat of vaporization for a cooling curve is going to be negative times N. Let me say that one more time. If you are drawing a heating curve, your heat of vaporization is positive because it is absorbing energy from the environment. When you are doing a cooling curve, your heat of vaporization is negative because it is releasing that energy into the environment. Okay, let's go to C. We have a temperature change, so it is mass times specific heat at that particular phase. We are in the liquid phase times the change in temperature. B is going to be the heat of fusion. Same thing as the heat of vaporization. In your heating curve, your heat of fusion would be positive. In your cooling curve, your heat of fusion is negative times the moles. And then your last section, that's going to be A, and that is a temperature change. So Q equals mass times the specific heat of the state that you're in. In A, we are a solid, so that's going to be S times the change in temperature. Okay, if I'm going a little bit too fast for you, pause the video so that you can keep up with me. Okay, let's do our calculations. We got to do E first. So E, like I said, is going to be Q equals mass times the specific heat of a gas times the change in temperature. So my Q will equal, the mass in the problem is 125 grams. The specific heat of a gas, take a look at your worksheet. It is going to be 1.850. And that is joule per gram degree Celsius, right? Because it's of a gas. Now, temperature, remember, it's a little tricky. We are starting off at 125 degrees. We are ending at 100 degrees for section E. So this is T initial. This is T final. So if it is final minus initial, that's how you're going to write it. Now let's do the math. 125 times 1.850 times. Now don't be concerned about the signs, right? Because it's going to matter. This is going to be times a minus 25. So we're going to end up with minus 5,781.25. This is in joules. Don't forget, you need to convert to kilojoules. Don't forget your minus sign. Move your decimal point back 3 spots. And that's kilojoules. Okay, let's calculate D. So D is going to be our heat of vaporization. That's negative now because it's a cooling curve. 40 kilojoules per mole times the moles. Let's calculate it. It's 125 grams of water. Put it over 1 gram of water, mole of water. 1 mole, 18.02 grams. Take 125 divided by 18.02, and you end up with 6.93. Whoop, let's be proper here. 6.94 moles. Okay, that's the number that goes up here. 94 moles. Do your calculations. Minus 40.7 times 6.94. You end up with a number of minus 282.458. And guess what? That's in kilojoules. Okay, let's get rid of all this work so I have some space. C. Temperature change. Q equals the mass, which is still the same, 125 grams. Now we have the specific heat of a liquid. That is 4.817, and that is going to be joule per gram degree Celsius. Now our temperature change for C. Initially, I'm here. Final, I'm there. So T initial, T final. So that is 0 minus 100 degrees Celsius. 125 times 4.87 times negative 100. We end up with minus 52337.5. That unit is joules. Convert to kilojoules. Minus 52.3375 kilojoules. We're almost there, y'all. Hang in there. B. Q equals the heat of fusion, negative, because we are a cooling curve, minus 6.02 kilojoule per mole times the same number of moles. We haven't changed how many moles we have. Okay, same number as up here. Do the math. Minus 6.02 times 6.94. You end up with minus 41.7788 unit kilojoules. Last section, A. Q equals the mass, still the same, 125. We need the specific heat of a solid, which is 2.06 joule per gram degree Celsius. Now we need to look at the temperature. It is just the section A. This is T initial. This is T final. That would be minus 22 minus 0 degrees Celsius. Okay? And remember, that's where I got these numbers, minus 22 and 0. Okay, let's do the math. 125 times 2.06 times negative 22 minus 5665 unit kilojoules. Joules. Convert to kilojoules. Minus, move your decimal point back 3 spots. 5.665 kilojoules. Okay, let's do some adding. So we have E plus D plus C plus B plus A. So let's put them in there. We have minus, don't forget the negative sign, y'all. 125 kilojoules. Okay, that is this number. Next number is D, minus 282.458. It's kilojoules. This number right here. Let me slide this over a little bit so I can get some more space. C, minus 52.3375 kilojoules. Right here. Plus B, which is minus 41.7788 kilojoules. Right here. And then the last one is going to be A, minus 5.665 kilojoules. Okay, let's add them up. I'll put them in parentheses so you can see that they were all negative. So minus 5.78125 plus minus 282.458 plus minus 52.3375 plus minus 41.7788 plus and minus 5.665. My answer is 300, and it's minus 388.02 unit kilojoules. That is the answer to number 3. Okay, let me back it out so you guys can see most of the problem all on the same screen. Okay, so as long as you follow the steps, you should be fine with these problems. Now realize that you're going to start and stop the problems at certain spots, and you'll find that out when you do the other problems, because you may not have to draw the whole cooling or the whole heating curve. Okay, so please make sure you're paying attention to what the question is asking you for, and I hope that was helpful.